hope everyone had a good Thanksgiving. Welcome to the lesson on heating and cooling curves. Before we begin with the heating curve, we're actually only going to do heating curves. The cooling curves are just the reverse. So we need to define two words that we're going to be using. So we've already defined kinetic energy. And kinetic energy is a measure of how fast particles are moving. And it's directly related to temp. So directly related to temperature. So if you increase the temperature, then you increase the kinetic energy. Okay, now we haven't talked much about potential energy. Okay, and in heating and cooling curves, potential energy is a measure of how close the particles are. So if the particles are moving further apart, you're increasing potential energy. If they're moving closer together, you're decreasing kinetic potential energy. And we definitely learned that in honors chemistry. Okay, so if we look at our heating curve, let me label the points. So A, B, C, D, E, F. So a heating curve shows how the temperature changes, or as you're adding heat, what happens to the temperature of the substance. Okay? And as we know, the substance always starts off as a solid, and then when it reaches the melting point, which is right here, and you should be labeling these things as I talk about it, when it releases the melting point, it starts to melt, and it becomes a solid and a liquid. And it takes a while for all the particles to return into a liquid. And when finally all the particles that are liquid at point C, the temperature starts to raise again, and it becomes just a liquid. And then it reaches what is known as the boiling point, so you should label this the boiling point. And at that point, it starts to turn into a gas. So it doesn't completely turn into a gas immediately, but it starts to turn into a gas. And then finally, at point E, it's completely a gas, and then the temperature of the substance just rises. And we covered this completely when we did this in the 10th grade. Okay, now, so what's happening during the line segments? So during AB, we see the temperature's going up, so that means that the kinetic energy is increasing. Now the potential energy stays the same. Okay, when they don't increase together. When one is increasing or one is decreasing, the other one is staying the same. Okay, during BC, this is when melting starts. Okay, and at that point, the kinetic energy is staying constant because the line is flat, but the potential energy is increasing because the particles are starting to move far apart. Okay, and at that point, this is important. At that point, sort of when the line is flat, the energy of the heat is going into moving the particles further apart. Okay. Then during CD, we see that the line is going up again. Okay, so then the energy there is going into moving the particles faster, or increasing the kinetic energy. Then during line D, so line D is when it starts to turn into a gas, or it's boiling. Okay, and then the energy is going into moving the molecules further apart. So that's DE. So there we have an increase in potential energy. The energy is going to move the molecules further apart. And then finally at E, they're completely a gas, and the line starts to go up again. So at EF, again, the energy is just going into making the molecules move faster, or increasing the temperature. So to summarize, and I probably would write this down, when the lines are flat on the heating curve, so when the lines are flat, okay, that is when a phase change is occurring. Here we're turning into a liquid from a solid, and here we're turning into a gas from a liquid. And there the energy that you're using to heat it is going into moving the particles further apart so they can change phase. And that's a change in potential energy. Okay? When the line is going up, okay, the energy there is going into move the particles faster until they reach either their melting point or their boiling point. And again, I didn't say this, but this is actually a heating curve for water. Water melts at 0 degrees Celsius and boils at 100 degrees Celsius. Now, I'm not going to go, in honors chem, we did a cooling curve. Cooling curve is just the reverse, okay? So it would go down. Instead of adding heat, you're going to remove heat, and it would start as a gas. So the heating curve would look like this. The cooling curve would look like that, okay? And the only difference is that instead of when you're removing the heat, okay, when the line is going down, the molecules are moving slower, or you're decreasing kinetic energy, okay? And when the line is flat here, it's turning into a liquid, so this here is the condensation point. And the energy being released is making the molecules move closer together. So this here is the condensation point. And when it's flat here, it's freezing, right? And the energy that you're removing, okay, is making the molecules move closer together. Okay. So we go to the back, and I'm actually going to leave it up here, but I'm going to just show you quickly the question on the back, if I can find my cursor. There it is. I erased the heating curve. There's a question, is what affects the slope of the line segments when temperature is increasing? So you should write what I talk about under that spot. So if we take a look here, the slope of this line here, so there's a greater slope, okay, than the line here. There's a lower slope. Okay, and the question is why? Okay, the slope of the graph in this, you need to write, okay, in that spot, okay, the slope of the graph, okay, is related to the specific heat, okay? And you say, but miss, it's the same substance, okay? But you notice that the temperature here is raising faster than the temperature happens here. It's raising here. That's why the slope is greater. So, this is the point here. The slope of the line is related to the specific heat, okay? The lower the specific heat, okay, the greater the slope, okay? Because that means if it has a low specific heat, it's going to heat up using less heat. So it just so happens, okay, that here this is water in the gas form, that the specific heat of water in the gas form is actually greater than the specific heat of water in the liquid form. We've been using this as 4.18, okay? But this line is, sorry, whoa, I reversed that, okay? My bad, I'm going to speak this again. So we know that the specific heat of water is 4.18, okay? You'll notice that this slope is going up. It's high, it's a greater slope than this one. That means, okay, that the specific heat of water in the gas form is actually lower, okay? Meaning water in the gas form heats up faster. Okay, so I'll say that again, okay? The slope of these lines is related to specific heat. The lower the specific heat, the greater the slope of the line. Okay, now we have one more question, okay? And that is, what affects the length of the line segments during the phases changing? So if we look at here, the sort of length of the line segments, when it's turning into a liquid, this is much shorter, okay, than when it's turning into a gas, okay? And that's because it takes less heat, okay, to turn this into a liquid than to turn this into gas. So the amount of heat that it takes to turn this into a liquid is called the heat of fusion, okay? So fusion is spelled F-U-S-O-N. And here is called the heat of vaporization, okay? And that's usually true for most substances, that the heat of vaporization, the amount of energy it takes to turn something into a gas, is usually greater, okay, than the amount of energy that when you need to turn it into a liquid. Now, what is this energy actually going into doing? Okay, so the energy that for heat of vaporization and heat of fusion is actually going to break the intermolecular forces to allow the molecules to move further apart. So in water, if we took AP Bio, you'll know that the intermolecular force between the molecules of water is hydrogen bonding. So in the heat of fusion and the heat of vaporization, that heat is going in to break the hydrogen bonds so the molecules can move further apart. But why this line is longer is that the heat of vaporization of water, okay, of turning something into a gas, is greater than it is to turn something from a solid into a liquid. Okay, I'm now going to upload this so that in the next video we can do the math associated with this.